Okay, hello everyone. My name is Zhao Jinyi and I come from China. My department is Industrial System and Engineering. So I'm doing my PhD career and my research area is vehicle routing problems, also known as VRP. So today I will give a talk on VRP and its variance problems. So if you have any question during my talk, please just stop me and ask your questions. Okay, so I will start from today's talk. First of all, I think you already know what VRP problem is. It's a set of combinatorial optimization problem and also it's an integer programming problems. It is just a set of problems that ask us what is the optimal set of routes for a fleet of vehicles to traverse in order to deliver to a given set of customers. So in this picture, we can see there are many customers and a depot. So the vehicle will depart from the depot and serve all the customers in several trips. So finally, we can design the route as this one. This for some kind of objective function. For example, we want to minimize the total travel time or total travel distance. We finally design some of this kind of routes, and we want to find out what is the best one. This is the traditional vehicle routing problem. However, in this years, many scientists they found out many different problems from the traditional one. Basically, we have two parts. First of all, we have vehicle parts, and secondly, the routing parts. For vehicle parts, sometimes we just need to design route for a single vehicle, and sometimes we need to design the routes for a fleet of vehicles. Like the fleet of vehicle can be homogeneous or heterogeneous. So the difference here are for heterogeneous vehicles, they have different settings. For example, they have different capacity or they have other fuel or electric vehicles. I think electric vehicles here is very different from the one we already know, because this years it is just a promising area, because lots of countries are more concerned about the carbon emission. So in order to reduce the total carbon emission, we want to use the electric vehicles to replace the fuel ones. But the problem here is the electric vehicles, they need to charge lots of times. So each time we charge, we can only serve some of the customers. Even sometimes we cannot go travel a day. So where and when we should charge our electric vehicle become the problem. So this is for the vehicle parts, and also the routing parts is also very important. Sometimes we just need to design, we set the vehicle can only perform one trip for a day, and sometimes each vehicle can perform multiple trips. So they are totally different problems and have different objective functions. So as I mentioned just now, the objective function can be just to minimize the total travel distance or minimize the total travel time. And sometimes for some maybe food delivery or online shopping company, they want to maximize the total profit. So, and also our vehicle routing problems can have some different constraints, and I will introduce them one by one. So first, I want to introduce what is the time window here. The time window is also a very common constraint in VRP problem. So let's see, For example, we are shopping on a online app like Lazada. They ask us to fill in a table that we want to be served within this time. Sometimes we just say, I'm at home from 9 a.m. to 10 a.m. Then the driver can only go to your home within this time. However, sometimes they maybe come earlier or later. Then it's okay sometimes, but in our problem, it's called soft time window. So for soft time window, it means we can arrive earlier or later than the time window, but we need to pay for a penalty. This is for the time window. And also we have pickup and delivery problem. It is mostly seen in the food delivery problems like Foodpanda or Grab, as we know. So each driver need to first go to the restaurant, pick your food, and then go to your home to deliver it. So for each route, we must guarantee that the driver will go to the restaurant first and then go to your home. The order cannot be swapped. So this is very important when we design the route using a computer, using a program. And also they must be in one trip. For one request, they have a restaurant and your home. It must be delivered in, must be designed in one route. So it means we cannot just pick up it and later another reader to send your food. It is impossible. So there's all the concerns that in pickup and delivery problem. And the third one is the capacity vehicle routing problem. Actually, this is quite easy and our benchmarks are very, very good in research area. So for capacity vehicle routing problem, it means that each vehicle has a limited volume. It means you cannot just put on a lot of things on it. So we can only hold an unlimited cargo. So this is the problem always combined with the multi-trip or multi-vehicle problem, because we cannot just serve all the customers in one route because of the capacity of the vehicle. And the last constraint I want to introduce is the time-dependent vehicle routing problem. It means in traditional problems, we always set the speed of the vehicle is a constant and always to be 1. Actually, it's not realistic, especially for the urban city. It is because we have morning peak hours and evening peak hours and off-peak hours. So in different time, the speed of the vehicle must be totally different. So we want to take this into consider and simulate the real life better. This graph is showing an example of for an arc from node I to node J. The vehicle travel on this arc have different speed, and the x-axis is the time, departure time from the I node. So if we departure from node I at within this time, then the speed of the vehicle will be v1. And if we departure in this time, then the speed of the vehicle is v2. What will happen if we departure from node I, for example, at this time, and it drive to somewhere, then the time goes to wij2. What will happen? The thing is, the vehicle speed suddenly become v2. So this is not good enough. Somehow it's not really realistic. But for research, we just to make it simply and somehow it can simulate the real life. Now I will introduce a problem. It is more like for research, and I want to from this work, I want to tell you what is the research like for vehicle routing problem, and also how we design and solve a new problem. In this problem, we consider a multi-trip and multi-vehicle time-dependent vehicle routing problem, and we solve it by an dynamic programming algorithm. So first, I will introduce it and giving the mathematical modeling for this new problem, and then I will describe how to use dynamic programming to solve it. So we know that for dynamic programming, we have two important parts. The first term is the state, and the second term is the transfer function. So later I will describe it in detail. And finally, I will give some experiments results and the conclusion. So for this problem, first we have n customers to be served, and we need to serve all of them. And we have k homogeneous vehicles. So remember, homogeneous here means they are the same. So their capacity is all to be Q. And each time we use a vehicle, we need to pay for a fixed cost P. So this is like a penalty of using a new vehicle. And every time the working hours for driver is from E to L, so we cannot work outside this time. And also for each trip, the vehicles can perform several trips, and each time is departure from the depot, go to serve some customers and go back to depot and so on. So for several vehicles, they all perform multiple trips, or one trip is okay. And each trip has a distance constraint D, so it cannot travel in more than D kilometers. Finally, for each customer, we have a service time and a demand value, S and Q. So demand value is according to the capacity Q. So in this route, for example, we serve 3 customers, then the total demand of these 3 customers cannot exist Q. This is for the setting. And our objective function is to minimize the total travel time of all these routes, all the routes for all the vehicles. And the total travel time plus the fixed cost. So it means if we use K vehicles, then we need to pay for KP penalty. The sum of these two terms are our objective. So we want to find out how to design the routes to satisfy all these constraints, and our objective function is minimized. Okay, is there any questions so far? Okay. Okay, so just now I introduced the time-dependent vehicle routing problem. So we already know that the speed of the vehicle is a step function, and we consider morning peak hours and off-peak hours. Statistical time in terms of dollar value. Yes, you can understand like this, because we add this two. The first one is recording $2, and the second one is also dollars. because P here, I know some these two, how to add them up, this is the problem, but P here is the value that we can decide. So this two, how to balance this two is inside of decision of P. Thanks for your question. Okay. Thank you. So I will continue. The step function for the speed of the vehicle is like sometimes very slow and sometimes very quick. So all these endpoints of time zone, we call it breakpoints. So breakpoints here is the speed breakpoints, and also we have another travel time breakpoints. How we get them is shown in this picture. We already know the travel speed here, but the resultant travel time becomes to be a piecewise linear function. Why is that? It's because the vehicle, as I said, if we departure at this time, let's say Wij1, then if from node I to node J, if it travels from I to J exactly end up J at time Wij2, then it will never experience a change of speed, right? So Wij1 is here. And if we departure from I later than this time, then we must experience from V1 to V2, the change of the speed. So V2 is much quicker than V1, then the travel time must be shorter. So the second part, later than Wij1, you can see the travel time is shorter and shorter until the Wij2. If we departure from node I at time Wij2, then the travel time, then the speed is always V2. So the travel time is the smallest. And for this time until Wij3, the speed of the vehicle is always V2 until sometime then the vehicle will experience from V2 to V3. Then the time will be longer. So this is like a piecewise linear function from node I to node J for one arc. Then this is only for one arc, but we know that for one route, there are many arcs together. For example, like we departure from depot and then go to customer 1, 3, and 4, like this, and then go back to the depot. So the arc here is 1, 2, 3, and 4. So how we get all the breakpoints, not only for one arc, but for this route? How we get it? Okay, first of all, why we need to get all these breakpoints, why they are important? It is because we want to minimize the total travel time. So if we only consider one arc, then the best solution, the minimized total travel time, must be one of these breakpoints, right? Because only they can be the best solution, not any points inside it. So we only need to consider the breakpoints, not consistent time. This will reduce the difficulty of the problem. And so now we only have breakpoints for one arc. How we get the breakpoints for a route? We use a backward propagation process. It means from the last two, the last one must be depot, right? Then the last customer we served, this arc is the last one. And now according to this arc, we already have some breakpoints. And then these breakpoints can be updated the previous customer, and then the previous one, and then so on and so forth until go to the depot 0, and we can get all the breakpoints for the whole route. Let's see a picture for an example to make it more clear. So first of all, we have there are 3 customers we want to serve in this route. So from ti+1 to d pi, we already have these 3 red breakpoints according to this arc. And using this as the arrival time at ti+1, we can calculate the corresponding departure time from node ti. Then they are these 3. And the green one are the green ones are the initial breakpoints for arc ti to ti+1. So now for node ti, we already have this 3 plus 3 together is 6 breakpoints for the 3 customers, the last 3 customers. And then the same process go to ti-1. Then we have totally 6 plus the yellow one are the initial breakpoints for arc ti-1 to ti. Then we have these breakpoints and so on until go back to the depot. We can obtain all the breakpoints for this whole route. So these breakpoints are the possible departure time for this whole route to get our optimal solution. We only consider these breakpoints as the possible departure time. This will be used later in the dynamic programming. And now I will introduce our mathematical modeling for this problem. So as I said, this part is the same, the settings of this problem. And now we use 1 to k to represent each vehicle we use. So the first one, the second one, and so on, until mostly we have k vehicles. And R is for each vehicle. For each vehicle, we can have R trips. Not necessary to be R. It can be only 1 trip or 2 trips. And also the second one have several trips and so on. So each vehicle performs multiple trips. And we use 1 to R to represent the number of the route. So now the objective function can be read as this formulation. It's like the second term is easier to understand. It's just the fixed cost times the number of the vehicles we use. So each vehicle, if we use it, then zk is 1, otherwise it's 0. So this is the penalty for the vehicles. And the first term is for all the trips, the travel time for all the trips together. And TT here means the departure time of a node. So here, this means for the destination depot n+1, the departure time is TT n+1, and the departure time from the departure depot is 0. So this term is for this trip, KR, for K's vehicle, R's trip, the travel time is here. And for all, we just sum up all the trips and for all vehicles, then this term, the first big term, is just represent the total travel time for all vehicle, all trips. And this is our objective function. And I just show some of the constraints. The first one is for each trip, the distance for all nodes, the distance for the route together, sum them up, cannot exist D. And the second one is for all the customers we serve in this route cannot exist Q. The demand of the sum demand cannot exist Q. This is because the capacity of the vehicle. And the third one is that for each customer I, it must be served in one vehicle, one trip. Cannot be, it is exactly one, because we cannot just don't serve it, or we also cannot just serve it twice. So this is must exist to be one. And the last one is for the time. This part is the resulted travel time according to our time-dependent formula. So we can get what is tau, what is s. So I will not introduce this part in very detail. If you are interested, you can go down and see the slides. Okay, so now let's go to the dynamic programming part. So before this, any questions for this formula? Is there any questions? Okay, good. So we know that the dynamic programming is a very useful algorithm. This is also very useful in the mathematical research or just for the engineering research. It's like, I think most of us like it because it can make a very difficult problem to be easier. Like when will we use the dynamic programming, is the whole problem is very big. For example, we now have n customers to be served, but the dynamic programming can just, if you know the initial for one customer, how to serve it, and then it can update how to serve for 2 customers, and then how to serve 3 customers, and so on until all n customers can be served. So this is like, first of all, we need to know what is the state, and then how to transfer from one state to the bigger one, and to the bigger one, and finally we got a whole state. So in this problem, we assume the state as dp tij v. So how to think about how to decide this state? First of all, we assume that we have 14 customers, and we will serve them in this order. We already know the order, but we don't know which one belongs to which vehicle and which trip. So the problem becomes we need to split it into several parts. For example, we split it first this part, and then this, and then this, and then maybe this. So split it. The first one is for vehicle 1, trip 1. The second one is for vehicle 1, trip 2. And the third one maybe the second vehicle, first trip. And this one is the second vehicle, second trip, and so on. Maybe only one node, and so on. So after we split it into several parts, finally we know how to how to serve all the customers, and we already designed the routes for all the customers we want to serve. Then the problem is how to split it, and then we can, in order to get the optimal solution. The optimal solution is to minimize our objective function. So we assume the state is like this. The first one is Ti. It means for Ti, we already know how to split from 0 to Ti. So the customer later than Ti, we don't consider it. We just consider this part. And we departure at Ti at time J. J is we use the breakpoint. It means J's breakpoint at this time. We get to Ti and then go back to depot. And from 0 to Ti, we use n vehicles. So this is the third term is the number of vehicles. Okay, so this auxiliary graph is used to understand our DP function. So DP function here, DP is just the dynamic programming. I use DP here. So the rows, like we have n customers, so they are from T1 to Tn, and the column is this nodes is for the breakpoints. So the first one is Ti at a very earlier time, and the second one is Ti at the maybe 9 a.m. and then 10 a.m. and then so on. Maybe the last one maybe 5 p.m. like this. So we have different time to departure and different nodes to be served. So at each state, we have different transfer functions. How to transfer from dp Ti minus 1 to Ti. How we get this? We call this transfer functions. We have different transfer functions from the small state to the bigger state. So it's quite easier for us to know how to split when we only have one node, right? If we only have one node, how to split? We don't need to split it at all. We just go departure from the depot 0 and then serve Ti and then go back. It's quite easy. And if we have two customers, then what happened? One way, if we just add T2 to this trip, then this trip becomes 0, T1, T2, and go back to 0. And the second possibility is that T2 is a new trip. By using the same vehicle, then we just from depot and go to T1 and go back, and then departure again to T2, and then go back to the depot again. So in this situation, the departure time has some relationship because we using the same vehicle. So we must guarantee that the time we departure from Ti must early enough for the vehicle to go back to depot and then departure to T2 at this time. So these two times have a relationship. If we satisfy this, then this transfer is possible. And the third situation is that we using a new vehicle for T2. So the trip is 0 T1 n plus 1 is the destination depot. And the second one vehicle go departure from the 0 and then go to T2 and then go back. These two vehicles. But using this situation, we need to pay for P, but we don't need to consider the time. So we don't know which situation is the best, but we can compare these three situations, which is the best. Then using the best, we can transfer to the second one, to the next T3, this DP3. Then for DP T4, DP T5, and so on, until we can get all the results for Tn. Then the minimized Tn is all the states for Tn. The departure time, we consider all the departure time from Tn and consider all the K vehicles we can use for Tn. And from all these results, we already updated and found out the minimized one. Then we found out the best splitting way for this tour, for this order. This is for our DP function. Maybe now you may think it's a little bit complicated, but maybe later you can just check out, because here I already draw it in this graph, and I think it's much clearer than what I said just now. So the first transfer function is when we update Ti, the Ti is we start a new trip, but not a new vehicle. Then we just need to consider if we add, we use this same vehicle, the time must satisfy something. So this is what we need to consider. And H here and J here satisfy the time. And we use the same vehicle, so here vehicle didn't change. Then Ti is just the count from Ti minus 1 plus the time from 0 to Ti and go back to the depot. This duration is this time. So for this trip, the relationship of this state to this bigger state is like this in the first situation. And the second one is when we use a new vehicle. So here we add a penalty for this new vehicle. And this part, the difference is like because we are using a new vehicle, so we don't need to consider the time from Ti minus 1 and the departure time from Ti. We don't need to consider that. So we just find out the best one. The best state for Ti minus 1, then the new vehicle starts maybe at the same time. It's okay because it's a new vehicle. And the third situation is maybe sometimes we go back to the dipole, but we need to take a rest. This rest is because maybe it's just the peaking hours, morning peak hour or evening peak hour. So if we departure again at this time, it's very expensive. So maybe it's better for us to just stay in the depot. So this ages is like we just waiting, because for the it's just you can say here we for the same Ti we update from one Ti to another Ti. The difference is the departure time are different, but the value should be the same. We just wait, and there's no penalty for waiting. And the fourth situation is this Ti maybe not just the just now we always departure from 0 and Ti and then go back, but actually maybe Ti is together deliver with others. For example, like this right one, then we together this trip is 0 to T3 and then to T4 and then to depot. It's like this. So Ti here, T4, this is Ti. Ti here is not the first node of this trip, but the last one. So if we design this new chip is from 0 to TP, TP plus 1, and so on to TI, and then go back to that port. If this is the current chip, then let's say, TI is come from TP, and then add something, and to update this TI state. It is because the time here for this trip, we already know. And then how we split from 0 to T minus 1 is the problem. Then we just use this states which we already updated, and then add this one can get the new state. And the last situation is same as just now. The fourth situation is just using a new vehicle. So from TP to TI, this trip is for using a new vehicle. So here we update from TP minus 1, DPT minus 1, but need to add a penalty P. These are all 5 different situations. And we can also say different transfer functions in this dynamic programming problem. It can be also used for different problem. This problem is very complicated, as you can see. There are many constraints, but we can use this dynamic programming to satisfy all of them. So also for some other constraints for other problems, we can also use this kind of idea to solve it. And now the problem is, if we have a Gen tour, if we already have this order of the customers, then we can split it using just now the dynamic programming. But how to generate the potential Gen tours, the potential order of the customers we want to serve, how to generate? We use an very famous algorithm, the heuristic method, the genetic algorithm. So in genetic algorithm, we assume or we simulate a population, maybe animal, maybe human beings. So initially, we have some initial human beings here, and they are the population is very small, and they are somehow not very good gene. But as this human being group, they have children, and then some good genes already resume, and some bad genes just we just cut them. Here we select two parents and then generate their children. And sometimes the children will get a mutation. So they mutate their gene, then can get a better one, maybe sometimes get a worse one, and they will not be selected to be the survivor when the population is too big. So the population sometimes reach the maximum value that we cite. Then we have to select the survivors, which considers the diversity of the population and also consider how their genes are. So here, decide what is good gene, what is the bad gene, is what their objective function is in our problem. The objective function, if their objective function is very small, then they are good. So we want to keep them, and then they can get children and so on. So after we using this process, we can generate very good Gen tours. Then this Gen tour, we use the dynamic programming to split, and then we can get how the route designing. then we know how to serve them. So how to initialize and how to mutate the children and how to survive, how to select the survivors. They are all very important, and many researchers has already designed all different kinds of methods to local search or to initialize or to select. So this part I just skip, and if you are interested, you can find out the papers on maybe this kind of paper. They are all very famous, and they can they are very generous, because for different problems, all of them can all this framework can be used to different kinds of problems. So now I will show you some results. First, we use the real-world data from the Coca-Cola company and send for them. They provide the real-world data from each day. Each day, these customers need to be served. So maybe you ordered 2 cans Coca-Cola, and others maybe ordered a big bottle or something like that. So we have the car, we have the demand of the customers, and also the distance of each customer, what they are, where they are, and here we can say there are some clustering method, clustering distribution in the real data. So this is because the residential area has lots of people, and some like zoo, no one will order food there. So it's not a residential area. Then here we can say there are some clustering distribution in the data. So how we use it? When we initialize the population in genetic algorithm, we consider this kind of distribution. So we want to use the clustering method to initialize. So we try 7 different clustering methods, including the famous KNN, K-means, and optics, and find out the optics is the best one. So we use it, and you can see the randomly, if we randomly select the order, it's the worst. So clustering is very useful here. And finally, we use this algorithm to initialize the population. And we subsample the data into only 10 nodes data. Then we compare with a commercial solver, the Groovy. So maybe you know the CPLEX more than Groovy, because CPLEX is more famous. Here we just compare with Groovy because it's quicker than the CPLEX. We use Groovy here, and the results are like, we set different penalty P, different capacity of vehicle Q, and different distance limited for a trip D. And if they are different, then our objective function cost is different. It's obviously. And the running time for Groovy is much longer than ours. It can be seen that the Groovy is still very slow. And for different, like this green part, for different capacity, if the capacity is bigger, then the number of trips is smaller. It's because we want to serve more customers in one trip, so that we can reduce the distance from depot and go back to depot. So we want to design the smallest trip. And also we have different penalty for a vehicle than the the number of vehicle may be different, 2 to 1, right? They are different. It's because if we use a new vehicle, it costs too much. Then we just use one vehicle to serve all the customers. Okay, so also we test on all the data sets provided by the Coca-Cola company. The customer is from 30 to 143. And the different of the settings come to different objective functions and different number of vehicles, different trips. But we think that the gap is not too big from the best solution we get and the worst solution we get. The solution are different is because for heuristic method, there are lots of randomly parts. So different randomly number, different initial solution will take us into different solution. It's like maybe the objective function is like this. Then sometimes if we start here, we can guess this best solution. But maybe if we start here, we can guess this best solution. So sometimes we just stuck into local optimal and cannot go out. So how to design, how to jump out are all very different and very difficult for our problem. And also we compare with the classical problem, the capacity vehicle routing problem. We compare with the benchmark and compare the running time. The blue one is the running time for our problem, our algorithm, and the yellow one is the benchmark algorithm. So if the customer up to from 600, I think, more customers, our algorithm can use shorter time than the original benchmark. It means our algorithm is better, and useful. Now I conclude this talk. So first of all, this research is motivated by the delivery company, the Singapore Coca-Cola company, and very thankful for them to provide our data. And we want to solve the problem that in urban city, when the speed of the vehicle is quite different from just to set it to be a constant one all the time, how to design the route under this situation. So the difficulty is how to split the tour, how to split it into multiple trips and multiple vehicles, and also how to decide each customer, what is the departure time from this customer. All of these things together make the problem very difficult. We found a dynamic programming algorithm to solve this problem. And and we also provide the mathematical model for this new problem. Also, the contribution is like we use the real world data and provide a benchmark for all the data sets. And also we found out that the initial solutions are very important, and there are some relationship, the clustering distribution in the real world data. So I think that's all. Thank you for your listening. Is there any questions?
Hello, excuse me. Can you hear me?
Yeah, can.
Okay, I'm online, and I'm a little confused about the solution. Why we just need to consider the breakpoint? So why the breakpoint? Or why the optimization solution only comes from the breakpoint?
Oh, it's for let's see. It's because for the first part, for each arc, if we only consider one arc, then the best solution, best departure time must be one of the breakpoints, right? Because they will never be some parts between them. The best one must be one of these breakpoints. If we only consider one arc, is that right?
Yep.
Okay, then one root is the combined of all these arcs one by one, and we know that the sum of piecewise linear function is still a piecewise linear function. So for this much complicated piecewise linear function, but the best solution is still one of these breakpoints. Cannot be between them. This is why we consider the breakpoints for this whole root using this backward propagation process.
Okay, I think I get it a little bit. Thank you.
Thank you. Any other questions?
Those on the side, any questions? Okay. How about those online? Any other questions? I actually have a lot of questions. I'll share with you after the break.
Okay.
Yeah, so thanks a lot again, Jingy, for this. I think this is at least also showing how research is being done. So, and also with this, at least you know Sao Jingy, right? So if any of you interested for research, at least you can speak to her. You can reach out to her for that. Yeah, and even like why she chose a figure routing problem as a research problem, and why this particular figure routing problem. Okay, yeah. So we'll stop the recording here, then we'll come back after the break at 7:30.